Hey, good morning. I'm going to go over 6.4, which is the central limit theorem today. I have the notes, which I attached, and you can take your notes on there. Or if you don't have those, you don't have a printer, that's fine. I got them in my journal. Okay, hopefully today the voice and me talking match up because the other day they did not, and that was a little distracting to me. I don't know about y'all. I'm sure y'all don't mind. Let's see. I can make this bigger. There we go. All right, so here is the central limit theorem. I went ahead and wrote down the notes in my journal, and I'll just talk about them as we go. So if you want to pause it, write things down, you can. So go ahead and pause it, and you can write these things down. And now I'll explain. So the central limit theorem, for all samples of the sample size n, where n is greater than 30, can be approximated by a normal distribution with mean of mu and standard deviation of theta over square root of n, where n is your sample size. So we can use the normal distribution if this is the case. N has to be greater than 30. You have to have 30 or more samples. No, I mean greater than 30, not or equal to. It has to be more than. So here are the practical rules. If the original population is not normally distributed, that means that it's either uniform, skewed, or something else, and you have more than 30 samples, the distribution of the sample means can be approximated by a normal distribution. So that is what we're looking for. If the original population is normally distributed, then the sample means will be normally distribution for any sample size. So you're checking to see, is it normally distributed? I don't know why I have such a problem with that. Normally distributed, or you have more than 30 samples. So you will use the central limit theorem. Number 3, though, if the original population is not normally distributed and n is less than or equal to 30, then the distribution of the S. I don't know what I was writing there. Of the apparently I just stopped in mid-track. Of the sample mean cannot be approximated by a normal distribution. And you cannot use central limit theorem. Oops, it's on my birthdays. Okay. So this is if for 1 and 2. Okay. 3, you can't even use central limit theorem. For 1 and 2, the mean of all values x bar is that mu x bar is mu, and then the standard deviation theta x bar is theta over square root of n. And then here's our conversion score. X minus mu equals theta over square root of n, which that looks really hard to see. So I wrote it over here better for you to see. Okay, so let's look and see. When can we use the central limit theorem? We can only use it when the original population is a normal distribution or n is greater than 30. Are you using a normal distribution with a single value x or a mean x bar from a sample of n values? Okay, so this is how we're going to determine which formula to use. If you're looking at an individual value from a normally distributed population, you're going to use this. And this was in 6.3. So I'm going to write up this set from 6.3 section. However, number 2, if it's a mean from some sample of n values, use the central limit theorem to find the z-score. So this is that new formula that we wrote on the last page. Theta x bar is a standard error of the mean. So you might see it as SEM. Two different distributions. So one of them is the distribution of the original population may be normally distributed. Or the distribution of the sample means will be normal when n is greater than 30, not greater than or equal to. That's a mistake. I found my... I always lose it. All right, so we're going to look at example 1 from the paper. I'm not going to have you write it down or anything like that. So computers are often used to randomly generate digits of telephone numbers to be called for polling purposes. So you have those digits. They're generated in such a way that are equally likely. The first graph shows the histogram of those 500,000 generated digits, which appear to be a uniform. So here is just the digits. They're uniform. It's a uniform distribution because they have an equally likely chance. Okay. So then we have n is 100 values. The mean of each of the sample, the mean for each sample of the 5,000 sample means are shown in the second graph. So this is the sample means. And see how the sample means are normally distributed. So even though we have this uniform distribution for the digits itself, whenever you do your mean, because you have 500,000 digits, but you're doing 5,000 samples, then this is a normal distribution. Okay, so that shows we have this one, the two different distributions. Remember how I was saying the two different distributions? So the original population may not be normal, but the sample means will be normal when n is greater than 30, not or equal to. All right, so let's look at example 2. When designing elevators, an obviously important consideration is weight capacity. An Ohio college student died when he tried to escape from a dormitory elevator that was overloaded with 24 passengers. The elevator was rated for a capacity of 16 passengers for a total weight of 2,500 pounds. Weights of adults are changing over time, and the following table shows the values of recent parameters of the population. So that's your population parameter. For the following, we assume a worst-case scenario in which all passengers are male, which could easily happen in a dormitory setting. If the elevator is loaded to a capacity of 2,500 pounds with 16 males, the mean weight of the passenger is 156.25 pounds. So that came from, this is your weight limit, and this is your passenger limit. So we are going to do weight limit. So we're going to write elevator. Weight limit is the 2,500. The passenger limit, also passenger E, is 16. So to find the mean, you would do 2,500 divided by 16, which is that 156.25 pounds. So that's your loaded capacity. So, but we have a little table here because we're going to talk about males and females, but we're going to focus particularly on males right now. The distribution. So we're going to make this little table. So the males in the population, because this is looked at ever so often because the weights change, But as of right now, the population parameter for the mean for males' weight is 182.9 pounds. And then our standard deviation is 40.8 pounds. And it's normal distribution. Okay, so our first question is find the probability that one randomly selected adult male has a weight greater than 156.25 pounds. So greater than that threshold that we had there. Okay, so we are going to use the formula because we're just dealing with the one individual. We're going to use number one. If it's an individual value from a normally distributed population, use this. So we are at z equals x minus mu over theta. So x is the one, no, that's our x bar. It's really like our x bar. So it's 156.25 minus our mu, which is 182.9. 182.9 is done. Looks fun. Over the 40.8. So when we do that, 156.25 minus 182.9 over 40.8. Negative 0.65. So then we need to do the table and look at, let's see, where did I put my table? So it's a negative z-score. Oh no, what happened? Messed up. Let's try again. Sorry. Good thing I got dressed and fixed my hair today. Okay, there we go. Negative 0.65. So negative 0.65.2578. So the area is 0.2578. But this is the area below. This is the area of negative 0.65. It's this area right here. But we want greater than. Okay, so we're actually going to have to do, because we are doing greater than, we're going to have to subtract it from 1. So 1 minus 0.2578. And that's 74.25. So 22, actually. 0.7422. That's what that's. Running out of space here. So that means, what's the probability that one randomly selected adult male has a weight greater than? That's about 75%. That's not very good, is it? Because if it's greater than, and you have 16 males that are greater than that, our threshold here, that means the likelihood of the elevator being overloaded is pretty high. So that's not good. Okay, so let's look at, I didn't give myself enough room. We're going to look at part B because that was part A, okay? So we're going to look at part B using the same information. Okay, so part B says, find the probability that a sample of 16 randomly selected adult males, that a sample has a mean weight greater than 156.25 pounds. So that means that the total weight is exceeding the threshold. And you have 16 adult males in there. Okay, so the things that we have the X bar is the 156.25. The mu of the population is 182.9. Standard deviation theta is 40.8. And then N here is 16. Okay, we can use a central limit theorem because this is a normal distribution. So remember, you had two things you had to check: normal distribution or that your N was greater than 30. Because the distribution of weights is normal, we can use the central limit theorem. So the central limit theorem tells us that we can use this other formula. So if it's a mean from some sample N values, use the central limit theorem to find the z-score. So we are going to use the z-score where it's minus theta over, or minus mu theta over square root of N. So this means 156.25 minus 182.9 over 40.8 over square root of 16, because we're doing a sample of 16. Okay, so we'll put that in the calculator. 156.25 minus 182.9 over 40.8 divided by square root of 16. Okay, so that is, our z-score is negative 2.61. So that means we need to look at the table. Negative 2.61, 0.0045. So the area is 0.00, what is it, 45? Let's see. 2.61. Go look at it again. Yeah, 45. So we are talking about being greater than that, though. So this area right here was 0.0045, but we want to find the area of it being greater. So we're going to subtract from 1. Oh, I don't need my phone. What am I doing? So 1 minus 0.0045. So the area, which is the probability that X is greater than the 156.25 is 0.9955. So that's not very good, is it? That means they either need to lower the number of passengers in there, the weight limit, or lower the weight limit. Okay, so let's look at, so this was whenever your original population is normal. Let's look at this next one. So example 3, men are typically heavier than women and children. So when loading a water taxi, let's assume worst case scenario in which all passengers are men. Based on data from the National Health and Nutrition Examination Survey, assume that the weights of men are normally distributed with a mean of 172 and standard deviation of 29. So our question is, find the probability that if an individual is randomly selected, his weight will be greater than 75 pounds. So let's write down the important information. So let's see. So we have use 172. Standard deviation is 29. So A is This is with the water taxi. So we want to see what is the probability. Let's see, this should be number 3. Example 3. So find the probability that x is greater than 175. Okay, so the first one is we're just dealing with one individual randomly selected. So that means, and since this is a normal distribution, we can use the z is x minus v over there. So that means we're going to do x is the 175 minus 172 over the 29. That's going to get my z-score. Okay. So I'm going to put this in the calculator. That's 3 over 29. So 0.1. So if we look at our table, 0.1, our z-score is 0.5398. I mean, our z-score is this, so our area is 0.5398. And we're talking about greater than, so we need to subtract from 1. So 1 minus 0.5398. So 1 minus 0.5398. So the probability that x is greater than 175 is 0.4602. Okay, so that's our probability. Okay, let's look at part B, which we're talking about more than one sample, more than one person is selected. All right, so I have a little bit of space, so maybe I can make it fit on here. Okay, so it says find the probability that 20 randomly selected. So we have n is 20. Find the probability that 20 randomly selected men will have a mean that is greater than the 175, so that the total weight exceeds a safe capacity of 3,500 pounds. So this is where we will use our central limit theorem. So this would be 175 minus 172 over 29 over square root of 20. Okay, so whenever we put that in, 0.4626. And then if we look at our chart, 0.6772. So our probability that x is greater than 75 when n is 20 is, what did I say? 0.6772. Oh, but we're talking about greater than, so we actually have to do 1 minus that. So it actually equals 0.3228. So this is the actual probability, because we're talking about greater than. If we were talking about less than, then it'd be the exact 0.6772. Okay, these types of calculations are used by engineers when designing ski lifts, elevators, escalators, and airplanes. Okay, let's talk about the rare event rule, interpreting results of the central limit theorem. If under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. Okay, so example 4 is going to be assume, let me show you all this. Assume that the population of a human body temperature has a mean of 98.6, as it is commonly believed. Also assume that the population standard deviation is 0.62 based on the information from the University of Maryland researchers. If the sample size n equals 106 is randomly selected, find the probability of getting a mean that is 98.2 or lower. Okay, so here's the information that we need to write down. So I'm going to write it down over here. Okay, so if we look at our normal curve, we are looking at mu 98.6, and we want to find the probability that x is, it says a mean of 98.2 or lower, so is less than or equal to 98.2. And since we have a sample of 106, we can use our central limit theorem, which we can find our z-score by doing mu over theta over square root n. Okay, so we'll plug in our numbers. So our z is 98.2 minus 98.6 over, so it's lower, right? So it's way down here. Over 0.62 over square root of 106. Okay, so we'll put that in the calculator, and you should get negative 6.64, which when we do the probability, let's look at our table. Negative, okay, so I need the negative one. 6.64. These don't even go to 6, but look at this. It says negative 3.5 or lower is that. So that means that the probability that x is less than or equal to 98.2 is 0.0001. Okay, so let me show you how you put this in the calculator. So that means that the probability is not high at all to really, really low. So let's look at the calculator. So we are going to use second bars, normal CDF. Is it normal CDF? Yeah. So our lower is the original that they have in there. Our upper is the 98.2. Oh, I messed up. Okay, it comes back. 98.2, and then our mu is 98.6, and then our theta, we're not going to use theta, we're going to use theta x bar, which is, remember, it's your standard error of mean, and that's going to be your, what we have on the denominator, the 0.62 over square root of 106. So I'm going to show you what that is. 0.62 divided by square root of 106. So you do not put in theta that they gave us. You're going to put in the standard error mean, which is all you have to do is, it's the denominator of our central limit theorem. So let me go back to bars, normal CDF. So lower is that, upper is the, where do we want to go, 98.2? And then 98.6 over 0.006. Okay, so when we put that in, that finds the probability that's less than or equal to 98.2, which is 1.315 e to the negative 11. So remember, e to the negative 11 means I'm going to move this decimal over 11 spaces to the left. So it's even smaller than that. So this is a rare event. So let's go to example 5. This is our last example. Cans of regular Coke are labeled to indicate that they contain 12 ounces. Data set 19 in Appendix B in your textbook lists measured amounts for the sample. The corresponding statistics is N equals 36. X bar is 12.9. So that's your mean. And then assuming that Coke cans are filled so that the mean is 12 ounces as labeled with a standard deviation of 0.11 ounces. Find the probability that a sample of 36, so that's our N, will have 12.19 ounces or greater. Do these results suggest the Coke cans are filled with the amount greater than 12 ounces? Okay, so since we have N is 36, we can use our central limit theorem. So we can find our Z by doing X bar minus mu over beta divided by square root of N. So we have 12.19 minus 12 over 0.11 over square root of 36. Okay, so when we do that, let's see what that is. 12.19 minus 12 over 0.11 divided by square root of 36. 10.36. Okay, so that's our z-score. So if we go to our positive z-scores, so it's 0.99999. So it's a really good probability, right? So our area is repeating. So it's a very good probability. So let's check real quick in the calculator. So we'll go to CDF, and we want it to be greater than. This is for less than, isn't it? Because it's like this, and we have 12, and this is 12.19. But we're talking about being greater. So less than is the 0.999. But we want it to be greater than. So we're actually going to have to do the probability that X it's supposed to be greater than 12.19, greater than or equal to, is 0.0001. Not a very good probability. So in our calculator, we'll do the lower will be 12.19. The upper is, we just put a bunch of 1 and then a bunch of zeros. And then we have 12. And then our new is this 11. Let's see if I can put it in here like this. Go by 6 because square root of 36 is 6. So that's 1.85 e to the negative 25. So move this over 25 spaces. And so that's a very low. So this is a rare event. Okay, the last thing we need to talk about, the correction for finite population. So finite population, it's not infinite, so it's finite. You can specify how many there are. So when sampling without replacement, sample size N is greater than 5% of the finite population size N. Adjust the standard deviation by using this. For most of our examples, we are sampling with replacement or the population is infinite. So this won't apply. Okay, so that finishes off our notes for the week. Make sure you work on your My Math Lab. If you have questions, email me. Let me know if you need anything. See y'all later. Oh,